So you are looking at graphics cards and notice something strange. Two cards might have similar CUDA core counts, similar boost clocks, similar everything on paper, but one consistently performs better and ages better. Most people assume it is the architecture, the specific GPU design. And sure, architecture matters. But today, I'm going to show you why one specification matters far more than any other in determining whether your graphics card ages gracefully or becomes obsolete overnight. And no, it is not what the marketing teams want you to focus on. Let's start with the basics. VRAM, or Video Random Access Memory. Think of it like a workspace for your GPU. When rendering a game, your graphics card needs instant access to textures, lighting data, frame buffers, and assets. Instead of constantly fetching from slower system RAM or SSD, the GPU keeps everything immediately accessible in VRAM. It is the difference between having tools on your desk versus walking to a storage closet every time you need a screwdriver. Bigger desk, more ready tools. Faster desk, quicker access. When talking about VRAM, there are really two specifications that determine real-world performance. First, capacity, how much VRAM your card has, measured in gigabytes. Think of this as the size of your desk. More capacity means storing more high-resolution textures without swapping. Second, bandwidth, how quickly data moves between VRAM and GPU cores, measured in gigabytes per second, determined by memory speed and bus width. Think of bandwidth as how fast your hands can move tools around your desk. Here is where things get interesting. In 2024, we're seeing games that genuinely require 10, 12, even 14 gigabytes of RAM at maximum 4K settings. The Last of Us Part 1, Resident Evil 4 Remake, Forspoken, Spider-Man Remastered, all push past 8 gigabytes at 4K with textures maxed. And this is only going to get worse. Game textures are increasing in resolution. Ray tracing adds substantial memory overhead, and developers are designing with next-gen consoles in mind. Consoles with 16 gigabytes of unified memory. Take the RTX 4060 Ti. NVIDIA makes two versions, one with 8 gigabytes of GDDR6, one with 16 gigabytes of GDDR6X. Same architecture, same CUDA cores, same boost clocks. The only difference is RAM. Yet in games at 1440p with texture-heavy settings, the 16 gigabytes version outperforms the 8 gigabytes version by 15 to 33%. The 8 gigabytes card stutters, drops frames, sometimes can't maintain playable frame rates because it is constantly swapping assets to slower system RAM. That is not an architecture problem. That is a memory capacity problem. Let me break down why this happens mathematically. At 1080p, you are rendering roughly 2 million pixels per frame. At 1440p, that jumps to 3.7 million. At 4K, you are at 8.3 million, more than 4 times the 1080p workload. Each pixel needs color, depth, lighting calculations. Higher resolutions also display higher quality textures more prominently, so engines load full resolution versions. The math is brutal. At 4K with ray tracing, you easily consume 10 to 14 gigabytes just for base rendering. Add ray tracing textures, shadow maps, reflections. Suddenly, 8 gigabytes feels impossible. Capacity is the big one, but there is another spec manufacturers really don't want you focusing on: bandwidth. Bandwidth determines how quickly your GPU accesses data stored in VRAM. It is the difference between having a massive library on your desk but only reading one page per second versus a smaller library you can flip through lightning fast. The RTX 4060 has 272 gigabytes per s. The RTX 4070 has 504 gigabytes per s. The RTX 4070 Ti over 1000 gigabytes per s. This isn't minor. This is a 2 to 4 times gap in how fast the GPU can actually use data. In practice, bandwidth limitations show up in specific ways. When running massive open worlds like Starfield or Cyberpunk 2077, with path tracing, your GPU needs to access texture, lighting, and geometry data constantly. If bandwidth isn't there, GPU compute cores end up waiting, twiddling thumbs while memory fetch is complete. This is why some cards with impressive boost clocks and thousands of CUDA cores still struggle in memory bandwidth intensive scenarios. The GPU is capable of doing work, but it is starved for data. On the NVIDIA side, We have GDDR6 and GDDR6X memory. GDDR6X, used in RTX 4070 Ti and above, uses PAM3 signaling that transmits more data per clock cycle, substantially higher bandwidth per pin versus standard GDDR6. The RTX 4060 Ti 16 GB uses GDDR6, while the RTX 4070 Ti uses GDDR6X. And even with the same bus width, the bandwidth difference is significant. AMD's RDNA 3 uses GDDR6 across the board, but compensates with larger caches and efficient memory compression techniques. Speaking of compression, this is where architecture does play a crucial role. Modern GPUs have sophisticated memory compression algorithms that reduce effective data size without losing quality. NVIDIA's Ada Lovelace architecture has improved lossless compression versus Ampere. This means the same VRAM can store more data, but here is the critical point. Compression ratios vary dramatically depending on content type. Simple textures compress well. Complex lighting and geometry, not so much. Better compression helps, but it can't substitute for enough raw capacity and bandwidth. Let's talk about The Last of Us Part 1 on PC, a game that terrified reviewers when it launched. At 4K with maximum settings, it consumed over 12 GB of RAM consistently. On RTX 3090 Ti and RX 7900 XTX with 24 GB and 20 GB respectively. Fine, but the RTX 4060 Ti 8 GB, it couldn't run the game at 4K max settings. Period. The game would crash, refuse to load textures, or throttle to unplayable levels. This wasn't a CUDA-core problem. This wasn't ray tracing. This was purely RAM capacity. And it is happening more frequently as developers optimize for next-gen console memory. So now you understand why RAM capacity and bandwidth are critical, which raises the question, why do manufacturers work so hard to bury these specs? Why do you see massive fonts for boost clocks and CUDA cores, while VRAM gets tucked in footnotes? The answer is profit. A card with 8 GB costs substantially less to manufacture than 16 GB. GDDR6X costs more than GDDR6. Wider buses cost more. By focusing on architecture claims and raw metrics, manufacturers charge premium prices for memory-constrained cards. And they get away with it, because most consumers don't know what to look for. This is where the mid-range market gets particularly tricky. Budget cards like RTX 4060 have excellent architecture but are hobbled by memory constraints. Only 8 GB VRAM and 272 GB per S bandwidth. The RTX 4060 Ti 8 GB falls into an awkward middle ground where it has enough compute power to run modern games, but not enough memory to do so comfortably at 1440p and 4K. Meanwhile, the 16 GB version costs only $100 more, a small price for dramatically better performance and longevity. But many consumers, seeing the 4060T badge, assume the 8 GB version is sufficient. We haven't talked about ray tracing yet, and it is a whole different ballgame. Ray tracing requires storing BVH data, bounding volume hierarchy, which can consume gigabytes of RAM. Each ray tracing effect, shadows, reflections, ambient occlusion, global illumination, adds overhead. Combine ray tracing with high resolutions, and VRAM requirements easily double versus rasterization. A game using 6 GB with rasterization might jump to 11 or 12 GB with full ray tracing at 4K. This is why the AMD RX 7800 XT with 16 GB often outperforms the RX 7700 XT with 12 GB in ray tracing, despite similar architecture. But what about DLSS and FSR? Don't these reduce VRAM usage? And the answer is, somewhat, but not how you might think. DLSS and FSR render at lower internal resolution then upscale, reducing raw pixel count the GPU processes. This helps bandwidth situations. However, texture data consuming most VRAM loads at full resolution anyway. DLS quality mode renders at 1440p for 4K output, but high-res textures still load into VRAM as if rendering at native 4K. Upscaling helps frame rate but doesn't fundamentally solve capacity problems. You still need VRAM for those textures. Let's look at a specific case study. The RTX 4070 Ti super launched with 16 GB of RAM, a subtle but crucial change from the standard 4070 Ti's 12 GB. In our testing and reviews across the web, this additional memory made a meaningful difference. Games that struggled on the 12GB 4070 Ti at 4K, with ray tracing played smoothly on the 16GB 4070 Ti Super. Not because compute architecture was dramatically different. It wasn't, but because additional memory headroom meant no texture swapping, no stuttering, no compromises. For a $100 premium, substantially better 4K performance. When buying a graphics card, you are not just buying performance for today. You are buying for the next 2 to 3 years, maybe longer. This is where understanding VRAM specs becomes critical. An 8GB card in 2024 might run most games fine today. But as new titles arrive, as texture quality increases, as ray tracing becomes more ubiquitous, that 8GB becomes an increasingly severe limitation. A card with 16GB gives you headroom for the future. You might not need all 16GB today, but you will tomorrow. Unlike upgrading CPU or adding system RAM, you can't easily upgrade GPU RAM after purchase. If you want to predict which RAM configurations will age well, look at PlayStation 5 and Xbox Series X. Both have 16GB of unified memory, with roughly 12 to 13GB available for game assets and graphics. This means developers are actively designing with 16GB available as a target. When they port to PC with higher resolution textures and more demanding settings, VRAM requirements only increase. A PC graphics card with less than 12GB operates below what games were designed for at console-equivalent settings. 16GB is the new baseline for comfortable 4K gaming. Let's talk about AMD's RX 7800 XT. It is one of the best examples of why memory specs matter more than architecture. This card uses RDNA 3, good but not quite as efficient as NVIDIA's Ada Lovelace in many scenarios. Yet the RX 7800 XT with 16GB consistently competes with or beats the RTX 4070 in many games at 1440p and 4K. Why? That 16GB gives it headroom the 12GB RTX 4070 doesn't have. At 4K with high textures, the 7800 XT loads full resolution assets without compromises, while the 4070 might start swapping to slower system. RAM. Memory specs trump architecture advantages here. On the budget end, we have RTX 4060 with 8GB and AMD RX 7600, also with 8GB. These are genuinely decent cards for 1080p gaming, and for 1080p 8GB is often sufficient today. The problem comes when you push to 1440p or 4K. Both cards show significant performance degradation at 1440p with texture-heavy games. Not because compute cores are overwhelmed, but because memory systems can't keep up. If you are buying budget and staying at 1080p for the card's life, 8GB might work. But if there is any chance you'll want higher resolutions, you are setting yourself up for disappointment. We haven't dug into bus width yet. The memory bus is like a highway connecting your GPU to its VRAM. A 192-bit bus transfers data on 192 lanes simultaneously. A 256-bit bus does more. A 384-bit bus even more. Bit bus, severely limiting bandwidth even with fast GDDR6. The RTX 4070 uses 192. Bit RTX 4070 Ti and above use 256. Bit, this is why RTX 4060, despite newer architecture, can actually be slower than RTX 3060 Ti in memory. Bandwidth, intensive scenarios. The narrower bus simply can't feed GPU cores fast enough. Some manufacturers advertise frame buffer sizes, sometimes confused with VRAM. In modern graphics cards, frame buffer and VRAM are essentially the same thing, the memory used for storing frames, textures, and game assets. Be wary of marketing that tries to distinguish these terms or imply different quantities. If a card has 8GB of memory, that is 8GB for everything. Frame buffers, textures, geometry data, the works. There is no secret extra memory hidden somewhere. The terminology might change, but the math doesn't. Let's talk manufacturing costs. GDDR6X memory chips are expensive, particularly high-speed variants used in flagship cards. A 16GB GDDR6X configuration costs substantially more than 8GB, and the memory bus costs more. A wider bus requires more pins on the GPU package, more PCB traces, more memory chips. This is why you see the same architecture in multiple price tiers, often differentiated primarily by VRAM amount. The RTX 4070 Ti is built on the same AD104 chip as RTX 4070, but with more memory-enabled and wider bus. That additional memory is a significant portion of the price difference. So what should you actually buy? Simplified framework incoming. For pure 1080p gaming with no monitor upgrade planned, 8GB cards, like RTX 4060 or RX 7600, are acceptable today. For 1080p hoping to upgrade later, aim for 10 to 12GB minimum. For 1440p gaming now and future, 12GB is minimum, but 16GB strongly recommended. For 4K gaming, 16GB is essentially mandatory, 20 to 24GB if you want full ray tracing without compromises. And regardless of resolution, more bandwidth is always better. Look for cards with wider buses when comparing similar VRAM capacity options. We're witnessing the death of 8GB as a gaming graphics card standard. It happened before with 4GB, which was considered generous just a few years ago, and is now completely inadequate for modern gaming. Same trajectory is happening with 8GB. If you are buying a new graphics card today with only 8GB, you are buying a card already showing its age at current requirements. In 2 to 3 years, it will be relegated to entry-level use at best. This isn't being dramatic, it is simple mathematics of game requirements versus memory availability. Before buying a new card, know how to monitor VRAM usage in your current games. MSI Afterburner with RTSS is the standard tool. Overlay your frame rate and add VRAM usage monitor. You'll see exactly how much memory your games consume at different settings and resolutions. If you are regularly hitting 90 to 100% of VRAM capacity, you are bottlenecked by memory, not GPU compute. This diagnostic information tells you whether your upgrade path should focus on memory capacity or raw GPU power. Here is a test you can do right now. Fire up a demanding game at your target resolution and settings. Load into a complex scene, a busy city, square, or dense forest. Check VRAM usage. Now lower texture quality by 1 or 2 steps. Check usage again. If frame rate didn't change but VRAM dropped significantly, you were bandwidth limited. GPU was waiting on memory. If frame rate jumped but VRAM barely changed, your GPU compute was the bottleneck. If both changed, you hit both limits simultaneously. This tells you exactly what to prioritize. Let's talk about how these specs get buried in marketing one more time. When NVIDIA or AMD announces a new GPU, what do they lead with? CUDA cores, stream processors, boost clocks, ray tracing performance, AI tensor performance. Memory, bandwidth, and capacity are mentioned, but often only in the spec sheet at the bottom of the press release. Why? Because they're acutely aware these are specs where budget cards show their weaknesses. RTX 4060 Ti with 8GB has the same CUDA core count as the 16GB version. On paper, nearly identical. In reality, performance gap is massive. If consumers understood VRAM properly, fewer would buy the 8GB version. If you are in the market for a new GPU, here is straightforward advice. First, determine your target resolution and how long you plan to keep the card. If it is 1440p or 4K, or keeping the card more than 2 years, prioritize VRAM capacity above almost everything else. A card with more VRAM and slightly slower architecture will outperform less VRAM with faster architecture in games you'll play next year. Second, don't completely ignore bandwidth. Cards with narrow buses like RTX 4060's 128-bit will struggle. Third, DLSS and FSR help frame rate but can't fix insufficient capacity. Fourth, buy for future games, not just today's benchmarks. Here is the truth, manufacturers don't want you to internalize. In modern gaming, your GPU's VRAM capacity and bandwidth are often more important than architecture. A slightly older architecture with abundant memory frequently outperforms newer architecture with constrained memory. This is why RTX 4070 competes with and sometimes beats RTX 4060 Ti 8GB despite fewer CUDA cores. This is why RX 7800 XT punches above its weight. This is why RTX 4090 with 24GB remains relevant years longer than RTX 4080 with 16GB. Memory matters, it always has. But in the era of 4K gaming, ray tracing, and demanding textures, it matters more than ever. Don't let manufacturers distract you with architecture marketing. Look at specs that actually determine whether your card plays tomorrow's games or ends up obsolete.